Today I am come back with a new topic, design and analysis of dual source vertical tunnel field effect transistor for high performance. Before we will start, first I will request you, please like, subscribe and share my channel. Let's start. Most of the students called me and told me about please make a video on a dual source vertical tunnel field effect transistor and give their advantages and code. Today we will discuss about one of the novel structure in vertical TFET is dual source vertical tunnel field effect transistor. First we will discuss why we use dual source vertical tunnel field effect transistor. Device such as TFET is being found to a replacement of conventional MOSFET to overcome the limitation of short channel effects and improve input characteristics of the device like steeper subthreshold slope, low subthreshold swing, low threshold voltage and high I-on-I-off current ratio. TFET is technically a substitute of MOSFET. Most of the disadvantages of the MOSFET are overcome by the TFET. TFET technology reduces the short channel effects because of the tunneling phenomena is different from the MOSFET. In case of TFET, we are using band-to-band tunneling mechanism, but in case of MOSFET, we were used thermonic emission. Due to band-to-band tunneling mechanism, the off current of the tunnel field effect transistor is low, so that the I-on-I-off current ratio of TFET is large as compared to MOSFET. The working principle of TFET is based upon band-to-band tunneling mechanism, which is responsible for the drain to source current, which further controlled by the gate biasing voltage. In this presentation, we propose and simulate a novel structure of a double source and U-shaped gate tunnel field effect transistor to enhance the on-state current and suppress the off-state current. The Silvaco Atlas simulation results show that the dual source vertical TFET has high on-state current and low off-state current compared with the conventional TFET and achieve a steep subthreshold slope. The advantage of using the dual source vertical TFET, it has high on current as compared to conventional TFET, and it also achieves low subthreshold slope as compared to conventional TFET. An optimized designed dual source vertical tunnel field effect transistor is proposed and investigated using technology computer aided design simulation Silvaco TCAD tool. In this PPT, in order to overcome these shortages, the proposed U-shaped vertical TFET is adopted and found with steeper subthreshold slope and enhanced on current. There is one drawback of the conventional TFET, that is low on-state current. To increase the on-state current, we have introduced a new technology or novel structure, that is dual source vertical TFET. It will enhance the on current and increase the I-on-I-off current ratio. In comparison to the conventional TFET, the U-shaped vertical TFET consists of U-shaped vertical dual source with the effective thinner channel length up to 8 nanometer, which meritoriously doubles the turning area and improves the drive current. In the proposed structure, the channel length is 8 nanometer. It will increase the tunneling efficiency of the device so that the device on current improves a lot. Figure in the next slide, that is this one. This is the proposed structure. Figure represents the schematic structure of proposed U-shaped N-type dual source vertical TFET. Uses HFO2 as a high K dielectric medium, and the effective gate oxide thickness is 2 nanometer and the physical gate length is 8 nanometer. The device consists of symmetrical dual source with effective length of 20 nanometer each side, with a drain height and width of 5 nanometer and 50 nanometer respectively. From the figure, you can note down that the source length in either side is 20 nanometer and the channel length is 8 nanometer, gate oxide thickness is 2 nanometer and the source thickness is around 50 nanometer and the drain thickness is around 5 nanometer. The gate work function is set as 3.8 electron volt and other parameter is varied accordingly. The doping concentration of the channel is around 10 raised to power 17 per centimeter cube, and source doping is P plus type. It is approximate 10 raised to power 20 per centimeter cube, and the drain doping is N plus plus type, which is equal to 10 raised to power 19 per centimeter cube. All the simulation are implemented in the Silvaco 2D simulator technology computer aided design TCAD with a non-local path band-to-band modeling model for determining the tunneling path. This is the proposed structure. Source doping 10 raised to power 20. I have already said you about these parameters. You can note down these parameters for designing and simulation of dual source vertical TFET. Let's move to the code. This is the code of dual source vertical TFET. Starting from the Go Atlas. Next is mesh definition. Mesh space dot multiple is equal to 1.0. This is a multiplying factor. Next, Xmax location starting from 0 and end at 48 nanometer. This means length of the device is 48 nanometer with different level of spacing. At the junction, I am giving the fine meshing as compared to other part of the device. And the Y meshing is starting from the 0 and up to the 75 nanometer with different spacing. 0.005, this means 5 nanometer to 0.5 nanometer, 1 nanometer, different value of spacing. After defining the meshing region, we have to define the region part. In the region part, I have started from the region number 1, material silicon with their positional parameter, X minimum 0 to X maximum up to the maximum value 48 nanometer, Y minimum 0 to the maximum value 75 nanometer. Region number 2 is for the oxide part, that is HFO2 with their positional parameter. Region number 3, 4, 5 and 6 is again silicon part with their positional parameter. Please note down every quantity very carefully, otherwise your code will not work. After defining the region part, next you have to define the electrode part. Electrode number 1 is gate. We are using the dual source, so that we have to use 2 source electrode number 2 and 3, and the electrode number 4 for the drain electrode, and their positional parameter are mentioned simultaneously. Next, we are doing the simulation of TFET structure. Next, you have to define the quantum tunneling region where tunneling took place. Next, we have to define the QT quantum tunneling X meshing region from location 0.015 to 0.05. The spacing is 0.5 nanometer. And the next is Y meshing, quantum tunneling Y meshing starting from 0 up to the 60 nanometer with a spacing of 0.5 nanometer. After defining the quantum tunneling meshing, next you have to define the device doping. In the doping region, we are using the 2 source region. The doping of the source region is equal to 1E20 with their different positional parameter, left side and right side. Next, you have to define the doping region for the channel region. We are using the doping of channel region is about 10 raised to power 17 with their positional parameter. Next, we have to define the doping region for the drain region. We are using the doping in the drain region is 10 raised to power 19 with their positional parameter. X minimum 0, Y minimum 0.065 and the Y maximum 0.070. Next, you have to define the contact region. You can also define the mass of an electron and hole. Next, I have defined the contact region, contact for the gate, drain and source. At the gate end, we are using the work function 3.8 electron volt. After defining the contact region, you have to provide the model to the structure. Next, we are using the model concentration mobility model, BGN model, SRH model, Shockley model, CVT model, Fermi model. Next is the quantum tunneling dot directory model is equal to Y directory, BBT non-local model. After defining the model part, you have to define the method statement. We are using two method statement, Newton and trap method. Next, you have to provide the drain voltage. The point to be noted that you have to give the drain voltage in the gradually manner, starting from the 0 and end at the 1 volt, 0, 0.05, 0.1 volt, 0.5 volt and the 1.0 volt. After giving the drain voltage, you have to give the gate voltage. First, you have to save the log file with the name of I had given VDS TFET 1.0. Next, solve AC frequency. We are giving this solve AC frequency to find out the capacitance of the structure. Next, we have to give the gate voltage starting from the 0 and end at the 1 volt with the step include 0.05 volt. Name is equal to gate. After giving the different voltage at the drain and source, you have to save the structure file by this command. Save outf is equal to the file name is this.str. The extension of the structure file is .str and the extension of the log file is .log. By visualizing these two structure file, these two log file and the structure file, you have to use the Tonyplot command. Tonyplot is the output command to observe the output in the waveform. Next, wait. When you run this program, you will find two files. One is the structure file and one is the log file. I will show you. This is my structure file. You can note down that the proposed structure is the same as that of simulated structure. Source length is about 20 nanometer. Both side. Gate length is 8 nanometer. And the thickness of the device, thickness of the oxide layer is 2 nanometer. I have already discussed about the parameter of this structure. One more is the log file. This is the log file in the linear form. You can change the log file in the log form. Right click on it, display, select the Vibrance scale is log. Okay. Now the y-axis is in log form, 10 raised to power minus 13 to 10 raised to power minus 3. The value of the on current is higher than 10 raised to power minus 4. That is the current in the milliampere. And the value of the off current is approximate in between the 10 raised to power minus 12 to 10 raised to power minus 13. And the point to be noted that the subthreshold slope is very low, so that the switching speed of the device is very good. Gate voltage is vary from 0 to 1 volt and the threshold voltage is around 0.25 volt. Let's go to the PPT. This is the table. Performance comparison of different work function for N-type dual source vertical TFET. As we change the work function of the device, we can note down that the threshold voltage is start increasing. This means if you are decreasing the work function, the threshold voltage is reached to the minimum value. And the value of the subthreshold slope is almost constant when you change the work function of the device. And the value of the off current is this and the on current is this. You can note down that the on current is start increasing if you are increasing the work function from 3.0 to 4.0 electron volt, and the on off current is high at 4 electron volt, and the average subthreshold slope is also increasing, and average subthreshold slope is also increasing from if you are increasing the work function from 3.0 to 4.0 electron volt, but it will be increased. This means you will get the optimized average subthreshold slope at 3.6 electron volt. It is about 3.47 millivolt per decade. This will show the switching speed is very good for dual source vertical TFET as compared to conventional TFET. I will show the curve also in the next slide. This is the transfer characteristic curve of IDS versus VGS for different value of gate work function from 3.6 to 4.0 electron volt. For N-type dual source vertical TFET, in which the channel doping is 10 raised to power 17 per centimeter cube and the gate voltage is increasing from 0 to 1 volt and the drain voltage is set at 1 volt. This is not the 1.5, this is the 1 volt. Figure 3 represents the simulated IDS versus VGS graph with the variation of gate work function from 3.6 electron volt to 4.0 electron volt. Due to variation in the work function, it is observed that from the figure, the threshold voltage of the device can be adjusted and optimized to the value of 0.15 volt. From the table, you can note down that the threshold voltage, the optimized threshold voltage value at 3.6 electron volt. The threshold voltage is calculated with the constant current method. If you don't know about the constant current method, it will describe that the minimum current is required to switch the device from off to on state, that is 10 raised to power minus 7 ampere per micrometer. This means the gate voltage corresponding to that current is equal to the threshold voltage. If you want to find out the threshold voltage by using constant current method, then the current voltage corresponding to that current 10 raised to power minus 7, that is that point, that point, that point and that point will show the threshold voltage of the device. If you are increasing the work function of the device, the graph is shifted from left to right. It will increase the threshold voltage. If you are reducing the work function of the device, then the graph is shifted from right to left. It will reduce the threshold voltage of the device. The electron concentration along the channel is increased as the gate work function is reduced up to 3.6 electron volt. This will help to increase the on current. And the graph shifted toward the left side, which leads to the high on state current recorded as 1.74 into 10 raised to power minus 4 ampere per micrometer. One of the characteristics we are discussing in this structure, that is transfer characteristics for variation in channel thickness for N-type dual source vertical TFET. The new proposed structure of dual source vertical tunnel field effect transistor consists of ultra thin channel. However, the channel thickness holds its importance to the performance of the device. The impact of the variation with the channel thickness on the device characteristics at VDS is equal to 1 volt is shown in the figure. As the channel thickness starts decreasing from 10 nanometer to 8, 7 and 5 nanometer respectively, then the off-state current will also increase proportionally. After the channel thickness is thin enough, the drain field increases the electron band-to-band tunneling rate with a static electric field. From the curve, you can note down that the minimum value of the off current is at when the channel thickness is 10 nanometer. If you are reducing the channel thickness, this will increase the static electric field and increase the off current up to 10 raised to power minus 7 ampere per micrometer. And the last characteristics we will discuss in this structure, dual source vertical TFET with temperature. The factor of the temperature includes the reliability of the device. In general, the ambipolarity conduction exhibits the smaller dependency over temperature, whereas the off-state current will depreciate when the tunneling will fall at the drain channel interface. The ambipolar current of dual source vertical TFET is very less, so that we did not include the gate voltage in the negative direction. With the rise in the temperature, the off current will also increases, which overall reduce the ion-I off current ratio as shown in the figure. This happens due to the phonon scattering and thermally generated reverse leakage current. Simply, if you are increasing the temperature, this will increase the phonon scattering in the device. This will generate more reverse leakage current in the device. You can note down from the figure, if you are increasing the temperature from 200 Kelvin to 600 Kelvin, the off current will start increasing due to the thermally generated reverse leakage current. The off current will start increasing at 200 or about 300 Kelvin is about 10 raised to power minus 12 to 10 raised to power minus 13. If you are increasing the temperature, it will increase the minority carrier in the device and increase the off current up to the 10 raised to power minus 8 to 9. However, the subthreshold slope will improve with reduce in the temperature as reported in the table due to the trap assisted tunneling current was suppressed at low temperature. When you increase the temperature of the device, it will impact on two factors. One is ion-I-off current ratio and second is subthreshold slope. If you are increasing the temperature, the off current start increasing. It will reduce the ion-I-off current ratio. And one more thing, if you are increasing the temperature, it also bitrate or deteriorate the subthreshold slope of the device. This means it will increase the subthreshold slope of the device. For better switching arrangement, we have to need a low subthreshold slope of the device. You can note down from the table, if you are increasing the temperature and the I-off current is reduced from this value from that value. This means it will increase the ion-I-off current ratio and the value of the average subthreshold slope at this one. At 200 Kelvin, the average subthreshold slope is 44 and at 500 Kelvin, the average subthreshold slope is around 40.3 millivolt per decade. My dear friend, this is end for today. If you like my video, please start from the 0 and end at the 150 nanometer with a different spacing. The variation in the X meshing spacing is large as compared to Y meshing spacing. You can note down that at the junction we are using the fine doping and other part we are using the coarse doping. Next is the reason. Reason number 1 is for the SiO2. X maximum 0.050, X minimum is not mentioned in the code. This means you have to understood that the minimum value of X is taken as X minimum. Same is for the Y maximum is 0.150 and the Y minimum is the minimum value of Y, it is 0. And the reason number 2 is 3, 4, 5. Reason is used for the silicon material. Reason number 6, 7 is used for the oxide layer, SiO2 layer. And the reason number 8 and 9 is used for the HFO2 layer. And its positional parameter for every reason is mentioned in the code. Next is the electrode reason. Electrode name is drain, gate, gate 1, gate 2. We are using the triple gate method. That's why we are using the gate 1 and gate 2. We have taken double gate so that we have used left side gate 1, gate 2 and the right side gate 1, gate 2. Next is the source electrode. I had mentioned every metal electrode with their positional parameter. Please note down every step very carefully. Next is the uniform doping of junction local. Next we have to apply the voltage, solve initial and the solve previous you can use, and the method Newton and trap. We had mentioned the maximum trap 10. V source is 0 volt and V gate is 0 volt when the device is in off state. When the device is in off state, we are applying the drain voltage from 0 to 1 volt. To make the device on, you have to apply the gate voltage. Next you have to create the log file and increase the gate voltage from 0 to 1 volt. Next we have to observe or see the output waveform with the help of Tony plot command. Next, I will define the various commands: output balance band, trap charges, surface potential, electron density, electron mobility. You have to mention this code to find out surface potential, electron density from the structure file. Next, you have to save the structure file and you can observe with the help of the Tony plot command. And the last one is quit. When you run this code, I'm running this code. When you run this code, you will get the two files, one file for the structure and one file for the log. This is the structure file, triple metal gate work function, and this is the HFO2 layer. This is the SiO2 layer for gate stacking. We have divided the source, drain and channel region, but we are applying the uniform doping, approximate 10 to power 19 per centimeter cube. I will show you log file. This is the log file. If you want to check the current in the log value, click on the log. OK. The off current is approximately 10 raised to power minus 16 and the on current is very high, approximate 10 raised to power minus 4. But the subthreshold slope is high. That look like. If we are changing the work function, then the subthreshold slope of the graph will change. Let's move to the slides. Next is junctionless vertical tunnel fill effect transistor GaN sensor working principle. GaN sensor work on the principle of conversion of concentrations of various gaseous molecules into standard electrical signal by using specific physical and chemical effects. When gas molecule of harmful gases like hydrogen and ammonia react with the catalytic metal surface at the gate contact, it brings in a change in the gate work function. We have already in the last slide in the H2 GaNs, I have explained how the gas molecule of the hydrogen atom affected the gate metal work function and its conductivity. Equation 1, this one, represents work function variability on account of absorption of pernicious gaseous molecules. Delta phi m is the change in the catalytic metal gate work function induced by the gas molecule reaction at the metal surface. Delta phi m depends upon the gate metal and the gas to be detected and is given by. The formula of delta phi m is this one. This is the continuous work function and minus this factor. This factor will depend how the gate work function modulate, in which R denote the gas constant, T is the absolute temperature, F denote the Faraday's constant and P denote the partial pressure of the gas. The relational dependency of partial pressure of a gas on its concentrations can be utilized to calibrate the device in terms of mole fraction of the gas in air. TFET shows 1.4 into VTH standard deviation than conventional MOSFET. TFET is more sensible device than MOSFET, and most of their attributes are evaluated by work function value of gate metals near the source where band-to-band tunneling mechanism take place. Thus, work function variation cause change in the threshold voltage and flatband voltage, which further alters the drain current I on and I off and its ratio. Next slide. The FET is used as a transducer, which transforms the shift of work function at the surface of the sensitive film catalytic metal into a corresponding electrical signal, a change in the drain source current. Simply, FET is used as a transducer which can transform the variation in the gate metal work function into the electrical signal, which results in the change in the drain current and the various factor also like threshold voltage and ion I-off ratio and sub-threshold swing of the device. Reaction of gas molecules at the catalytic metal gate surface results in the change in the work function of the gate metal, which further cause change in the flat band voltage due to the additional band bending. Flat band voltage change results in the shift in the surface potential, threshold voltage, and the drain current of the device. Thus, by monitoring the change in the threshold voltage, I/O of ion, and subthreshold slope, it is possible to detect the presence of the gas molecules. For example, oxygen, hydrogen, ammonia, and other hydrocarbons using suitable catalytic metal gate work function. The dependency of the flat band voltage VFB on work function is represented through equation 2. How the change in the flat band voltage vary with the change in the gate metal work function. VFB is equal to phi m minus phi s plus minus phi m, where phi m denotes the metal gate work function. We know that. Delta phi m denote the gate metal work function variation. Delta phi m is equal to the metal gate work function without gas molecule minus gate work function with gas molecule. And phi s denote the work function of silicon given by the equation 3. Simply phi s denote the work function of the silicon material. We know that the work function of the silicon material is equal to Eg by 2 electron band gap plus electron affinity minus Q delta Fp for n channel device. The variation in threshold voltage affect the subthreshold current of the device, which change the I/O current represented by the equation 4. The equation of the subthreshold current is equal to this one. I naught E, this one factor VGS minus VTS divided by eta VT into me 1 minus e की power minus VDS by VT, in which I naught represent this one. W by L, mobility of the electron, oxide, thermal voltage here e की power minus 1.8, and the VT, thermal voltage. VGS, VDS and VT are the gate to source, drain to source, and the thermal voltage of the device respectively. L and W denote the length and the effective width of the transistor respectively. QX denotes the oxide capacitance of the gate. Eta denotes the coefficient of the subthreshold swing, and mu n denote the electron mobility. Now we will talk about the result. Figure A, B and C. This one. A, B and C represent the effect of variation of 50 milli electron volt, 100 milli electron volt, 150 milli electron volt and 200 milli electron volt in work function on the drain current for cobalt, molybdenum and the palladium respectively. As can be seen in the figure that the I/O current is changed exponentially when the work function is changed in milli electron volt, and it is clearly show that the effect of the gas molecule is much higher on I/O as compared to ion. Thus, subthreshold region offers much higher sensitivity along with low power operation, thus providing low cost gas sensor device. In the junctionless device, if you change the gate work function, then its off current will be changed. But in the doped and the charged plasma device, if you are changing the gate work function, the most effect of the changing the gate work function on the on current. But in case of junctionless device, by changing the gate work function, produce the more effect on the off current of the device. With increase in work function, we can note down in the figure, with increase in the work function, the steepness of the energy band diagram of source channel interface decreases, leading to a reduction in the tunneling probability to the conduction band. By reduction in the tunneling probability, the off current start decreasing. We can note down that in the figure that if you are increasing the gate work function, the tunneling probability is reduced in the off state, which result in the decrease in the off current of the device. The reason behind is that the duality of a high enough potential barrier is in the prevention of tunneled electron from overwhelming it, or allowing only those with adequate energy to flow towards the drain directly from the channel. Due to the reduction in the tunneling probability and increase in the barrier at the source channel interface. Only the high energy electron can cross from the source to the channel region. This will result in the reduction in the off current of the device when the device is in off state. Thus, only those electrons having high enough energy become part of the band-to-band tunneling mechanism in the off state. This causes the exponential decrement in the off current with increasing work function. The on-state current is not much influenced by the work function variation. You can note down in the figure. The variation in the on current is very less as compared to the variation in the off current of the device. This is the sensitivity comparison. Sensitivity calculation of the junctionless vertical TFET based GaN sensor using cobalt first table for the cobalt gate electrode. This one. Second table for the molybdenum gate electrode, and the third table is for the palladium gate electrode. And the third one is used for the hydrogen gas sensing, and the above two metals are used for the ammonia gas sensing. From the table you can note it down that without gas you will get the current up in the 1.83 into 10 raised to the minus 10. If you are applying the gas molecule at the gate electrode, the off current of the device is decreasing. You can note down in the figure. Both for the cobalt and the molybdenum electrode. When without gas you are getting the high off current. When you are applying the gas molecule at the gate metal electrode, then the off current start reducing. It will reduce up to the 10 raised to power minus 14 in case of cobalt metal electrode and 10 raised to power minus 11 for the molybdenum gate electrode. But in case of the palladium gate electrode, you are getting the off current around 10 raised to power minus 14, very high without gas molecule. If you are applying the gas molecule at the gate electrode, the off current is reducing very fast. It will reduce up to the 10 raised to power minus 16 ampere per micrometer off current of the device. You can note down that there is no change, approximately no change in the on current, either in the case of cobalt, molybdenum or palladium electrode. By reducing the off current, we are increasing the I-off ratio. This means if you are applying the gas molecule at the gate electrode, the ion-I ratio is increasing. It will be increased up to the 10 raised to power 6 to 10 raised to power 10 in case of cobalt electrode, and in case of molybdenum electrode it will increase up to the 10 raised to power 4 to 10 raised to power 7, and in the case of the palladium gate electrode, the off current is increased, the ion-I ratio is increasing up to 10 raised to power 10 to 10 raised to power 12. Next is the last one is the future scope. Further optimization may be done in terms of gate engineering and the channel related parameters to implement a cost effective low power GaN sensor with less on-chip area, studying the device behavior in the subthreshold region, provide scope for enhanced sensitivity of the device GaN sensor. Second, the vertical architecture with increased gate controllability and the absence of the sharp doping gradient makes junctionless vertical TFET a promising candidate for future research on GaN sensing device. My dear friends, this is end for today. You can do the further